Very much. I've been reminded that it's only me between you and the wine, and so I will, if nothing else, be brief. What I'm going to do is two things. First of all, talk a little bit about landscape scale decision making and give some examples of how hydrological research might inform those kinds of decisions, kind of policy decisions that we're charged with informing. And then I'm going to talk about a new program, a new NERC funded program called Hydro-JULES, which is about building an open source community model for simulating the water cycle and for linking models of the water cycle to atmospheric models, ocean models and other models in the Earth system. So I'm Simon Dadson from the Centre for Ecology and Hydrology and also from the University of Oxford. A few examples, mainly to look at, and these are themes that have emerged over the course of our discussions today, around the role of scale, uncertainty, and how the truth varies with scale, as we were hearing in the questions relating to the previous presentation. Looking also at the ways in which we might need to use our models of natural and human systems and look at the interaction between those different models, to motivate really the need for an integrated model of the water cycle. It's not necessarily the case that the examples I'm showing are precisely the examples which motivated the NERC program, but I think they illustrate some of the questions that we need to get answers to in order to help inform the policy decisions that need to be taken. And so I'll spend the last half of the presentation talking about this new community modelling framework which we've been developing over the last year or so, and which will continue to be developed over the next 4 years. So the role of scale in looking at the hydrological impacts on landscape decisions is extremely important, and the example I want to draw on here is an example that has emerged in our work looking at the efficacy of natural flood management interventions. One of the things which has jointly, one of the issues which has jointly been driving policy interventions in relation to flood risk management has been not just variability in the climate, which is illustrated on the left-hand side of the plot. You can see over the period from about 1870 until the present day a large range of variability in flood-rich and flood-poor periods, but also variability in land cover, variability and changes over that period of time in forest cover, in the state of our rivers, the connectivity of rivers to floodplains, and other mechanisms which are important in driving flood risk. One of the interesting policy questions which has been discussed in some of the talks previously and in the questions that have followed from those is, can we, rather than manage flood hazard at the point at which that hazard is experienced, that is at the level of the household or the level of the river or the level of the piece of infrastructure which is suffering from the flood, can we manage that flood hazard by making an intervention somewhere further upstream in the catchment, rather than dealing with flood at the place where the problem arises? Can we manage that form of flood hazard higher up in the catchment by making interventions which might be cheaper, which might be better integrated with other landscape processes, which might have co-benefits for biodiversity, for carbon sequestration, for economic productivity or for livelihoods. And so we put together a review of the scientific evidence for the efficacy of this process, this idea of using a set of landscape scale decisions which are taken in the wider catchment, rather than a set of decisions which are taken to protect individual assets against flooding. I won't go into the details of everything that review of evidence found. It's been published for a year or so now in the Proceedings of the Royal Society. But it looked into a series of processes which are commonly implemented, or a series of mechanisms which are commonly implemented to deal with natural flood risk management. And you can see on the left-hand side of the screen the kinds of processes which are typically relied upon to implement natural flood management. They're things like managing infiltration and overland flow, so managing the way in which water flows through the headwaters of streams, managing the connectivity of those runoff generation units as water moves downstream and the way in which water is conveyed through the catchment, and managing the way in which that water is delivered to the floodplain and the opportunities for storing and slowing its passage through the floodplain. And so you can see that in the context of this workshop, and that's really the reason for referring to this piece of work, in the context of this workshop there's a huge range of different landscape decisions which need to be made in order to take advantage of this potential for natural flood risk management. And what we discerned from the review is that actually the effectiveness of these particular mechanisms, it might be things like planting trees in the headwaters, we've heard lots about that today. It might be things like putting large woody debris dams on headwater streams to try and slow the flood wave down as it passes through the landscape. It might be things like reconnecting rivers to their floodplains or providing off-channel storage ponds to store the top of the floodwater so it does less damage. One of the resounding conclusions which came from this study is that what you do and its effectiveness depends very clearly on the type, the magnitude and frequency of the flood that you're trying to avert, and it depends on the scale of the catchment, the size of the catchment that you're trying to manage. And so it's important, I think, the insight to draw from this in relation to the workshop that we're having here today and over the next few days, is that a lot of the impacts of the decisions which we're taking are very specific to the magnitude and frequency of the environmental variability that we experience and that we're having to manage, and are specific to the scale of the system which we're trying to study. You can see in this sort of cartoon distillation of the findings that we had, that for large floods in large catchments, the most effective way of reducing flood peaks is to have some kind of wetland off-channel storage or something which is capable of storing a large volume of water. For dealing with relatively small magnitude floods in small areas, planting trees, dealing with soil quality, managing infiltration can be quite effective. But the effectiveness of that intervention diminishes as you move downstream and as you move to larger and larger catchments. It's an interesting conundrum. It's an interesting question to pose as a mathematical question or as a physical question. And it's not one I'm going to come back to, but it's one I'd be very happy to talk to anybody about if that fires off any interest amongst the mathematicians here. Another example stems from exactly the same question around water flowing downstream, but here it's looking at how we actually take the impacts that we see, or the systems that we think are likely to be impacted by climate change or land cover change or any other sort of biophysical change, and how we actually frame the decisions and how we frame the decision-taking process around dealing with uncertainty and dealing with the variability in those systems. Typically, it has been the case that we've developed scenarios of how the future is likely to pan out. We've heard about various efforts by the IPCC to articulate scenarios of what the future might hold, turn those scenarios into some kind of representation which is compatible with our models of climate prediction, greenhouse gas emission trajectories, for example, or trajectories of representative concentrations and so on. Feed those through a climate model, downscale them using a different sort of climate model, or perhaps even the same sort of climate model, feed those into an impacts model, and feed those impacts into some kind of socioeconomic model or hazard model. And as you go through this cascade, this is a diagram from Wilby and Desai's paper in 2010. As you go through that cascade, the plume of uncertainty increases, and almost to the point where the amount of information that's available, the spread on the different trajectories through the system becomes so pathologically large that either almost any decision is possible and therefore no decision is taken, or almost any decision is possible and the decision is taken which is most politically suitable at the time. And we've seen lots and lots of examples of that sort of thing. So what we wanted to do in this next study, which I'd like also to draw on for some inspiration in the workshop, is to think about how we deal with this pathological cascade of uncertainty in the face of a large range of possible futures. And this is an example here. Just the plots on the left-hand side are some results from a study which followed on from the previous round of UKCP climate projections, not the UKCP 18 projections which have just been released, but the UKCP 09 projections, looking at the hydrological consequences of those projections. And you can see in the series of diagrams there that, and this is showing via a colour scale, the change in river flow amongst, I think it's 11 simulations of potential futures for the UK. You can see a wide range of responses from the point of view of the magnitude of change, but also a wide range of regional responses. There's an awful lot of signal or noise or variability, at least, in what the system is producing. And that is useful if you have models that can cope with uncertainty, or useful if you can have models that can cope with wide ranges in variability. It might tell us something about our need to plan for an uncertain future, or a need to plan for a wide range of scenarios when we're dealing with something like water resources planning. But it also calls upon us to find different ways of capturing that uncertainty and of making decisions in the face of those wide-ranging possibilities. And on the right-hand side is an attempt to do that by creating not a projection of what we think the future might hold in relation, in this case, to phytoplankton blooms, so large harmful algal blooms floating down the River Thames in the summer when it gets hot. The algae in the Thames and lots of other rivers and lakes and so on reproduce and become harmful to aquatic life and to water quality for drinking water and various other things. And so it's a very important operational question and policy question to know what the risk is of these harmful algal blooms, and to know how that risk is likely to change in the future. And so instead of producing a spaghetti plot of lots of different possible trajectories, here it's depicted as a risk surface showing how the changing risk of harmful algal blooms is likely to alter in the future in response to changing precipitation and in response to changing temperature. The interesting thing about this is that factored in to the climate change response in relation to harmful algal blooms is also an implication that land cover is responsible for delivering nutrients to the river channel and for dealing with the amount of nutrition that the algae species themselves have in order to grow. And one of the interesting conclusions that came from this study is that whilst there is a strong connection between climate change and the risk of harmful algal blooms, in this case in the Thames, the effect is just as strong from land cover change and is even stronger from phosphate reduction in wastewater treatment works as you move along the Thames. The sort of signal that might not emerge if we looked just at the climate change trajectory, but which is actually order of magnitude equivalent to the climate change signal, and which from the point of view of making these kinds of landscape scale decisions is really important, because it's a different group of people that controls phosphate emissions from wastewater treatment works than it is that controls the broad-scale changes in temperature and precipitation over the next 30 years. And so the decision is vested in a different public, and our mechanisms for engaging with that public need to reflect that. So those are just two what I think are interesting environmental questions which call upon us to have a more integrated approach to environmental decision making in the water sector. And it's those kinds of questions which have motivated the genesis of the program called Hydro-JULES. Hydro-JULES is aiming to do lots of things, but the principal aim is to produce a fully integrated open source coupled model of the terrestrial water cycle, and it's going to be linked to the joint UK land environment simulator, which is JULES. Now JULES, as many of you in the audience will know, JULES is the land surface scheme which sits at the bottom of the Hadley Centre, the Met Office suite of climate and weather prediction models. And so it's important that we represent the water cycle in a way which is compatible with Earth system models, compatible with weather prediction models. But it's also important that we represent all of those different interlinked components of the water cycle, which all acting together produce the kinds of effects, the kinds of interactions that I've been talking about previously. This particular program falls within the Natural Environment Research Council's national capability strand of activities, and so it's designed not just to achieve scientific results in its own right, but to enable a community to form around this particular activity and to enable us to address collectively the kinds of science questions that can't be done without a community model. Comes at an interesting time. We see a suite of hydrological models which are typically calibrated on particular catchments where there's lots of data, the sorts of hydrological models that are used to underpin decisions made about flood risk in the UK or about nutrient loading in streams. But we're also seeing an increased computing ability to run large-scale land surface models over large areas, and the two meet with different imperatives. Land surface models are essentially derived from being the boundary layer schemes at the bottom of weather forecasting and Earth system models, and so they're designed to close the water, energy, carbon budgets, and that's very important. Hydrological models developed for particular catchments where there's lots of data are often very well tuned, but that comes with a price, and that's that they may not operate reliably under conditions for which they've not been tuned, i.e. under conditions of global change. And these sorts of models are converging on commensurable scales. We're looking at global models of, it says half degree there, but quarter degree is now more typical for a global model, now down even to 10 kilometre or 1/10 of a degree. And in our case, for a national modelling capability in hydrology, a resolution of around 1 kilometre for that sort of modelling. The kinds of questions that this system is motivated by are to look at how hydrological systems will respond to current and future climate variability, particularly in data-sparse regions where we don't have as many measurements as we need to produce calibrated models, and under non-stationary conditions. That might be non-stationarity of climate. It might also involve changes in land cover and other sorts of land management. Increasingly, the second point there, increasingly weather forecasting models resolving convection at finer and finer resolution using more and more detailed process representations, and this providing an opportunity for hydrological models to take advantage of those new streams of information which are coming in from the high intensity convection resolving models that are now being routinely run by the Met Office to produce weather forecasts. Of course, alongside that improvement in resolution comes an increase in uncertainty, and matching our appreciation of that uncertainty in the way it interacts with the hydrological processes in the land surface it provides a very interesting opportunity to understand those process responses. Lots about climate change, but also looking at the response of hydrology to land use change and land management. A lot of the presenters in the talks today raising this question of what happens to our environment if we plant trees across large swathes of northern Britain or other parts of Britain, as some of the other simulations have indicated. The impacts on hydrology are rather difficult to discern unless you have a national scale model which is capable of resolving the biophysical interactions of plants with the soil and therefore with the water cycle. And so that's another of the imperatives behind this program. Also the need to connect different types of flood risk, fluvial, pluvial, coastal and groundwater flooding, which happen individually but which concatenated produce risks that are to some countries around the world, the Netherlands for example, are existential, and when you think of storm surge related flooding in the northeast and in London, are very high on the national risk register in relation to the UK. Some additional scientific motivation questions, and again I stress these are not necessarily questions that we during this programme will completely resolve the answers to. It's intended to be far further reaching than that. It's a community collaborative programme, and the idea is to create opportunities for people in the hydrological and other communities to come together to address these problems. Looking at consequences for biogeochemistry and nutrient cycles, clear consequences for nutrient cycling, nitrate, phosphate and so on in the UK, important aspects of our water quality, but also the impacts that changing climate, changing land cover, changing land management have on nutrient delivery to ocean basins, and the consequent impacts on the biogeochemical circulations globally. And then there's a couple of points there which are really sort of desirable properties of the system or abilities to use new technologies. One is data assimilation, which has been mentioned before. This is the idea that we have a very large number now of new data sources. They may be in situ sensors that have been newly developed. One that we're looking at is a cosmic ray detector of neutrons in the soil to infer large area soil moisture measurements. Other sensors, Earth observation, satellite-borne, airborne sensors, providing unprecedented amounts of information which can help nudge models back to the correct state, or which can help us to assimilate the parameters of, or can assimilate that data in order to calibrate parameters in the models more effectively. Also a program of work to look at uncertainty in hydrological models and to try to diagnose where that uncertainty lies in the process chain, principally to quantify it, but also to target further research to the relevant processes. So this is a program which is about a year in. It's a 5-year program and we're about a year in, and a lot of the essence of the way in which it's been constructed is as a community model, and so a series of stakeholder consultation workshops, stakeholders here being principally members of the research and academic community, it being a national capability project in that sense, but also Environment Agency, Flood Forecasting Centre and some of the sort of problem-facing end users in the policy and regulatory world. Those consultations have identified 5 process-related areas, which I'd be very happy to talk to people about, but which are dominating our science agenda. One is groundwater, representation of lateral transport in groundwater, heterogeneous properties of aquifers and so on. Soil hydraulics, the pore spaces in soils typically range over some crazy number of orders of magnitude, probably 12, 14 sometimes orders of magnitude, and so rethinking the kinds of theories that we use to relate runoff production to the state of soil moisture, taking account of flow at various spatial scales. Thinking about evaporation, particularly thinking about evaporation from vegetation canopies. A lot of the science behind the natural flood risk management interventions that I talked about before is around how you influence the balance between precipitation, evaporation and runoff, and so improving our models of evaporation. Fluvial inundation, groundwater inundation and so on, and importantly representing anthropogenic influences, not just the effects of changing water environment on dams, abstractions and irrigation, but in many river basins around the world, abstracted water used for irrigation is order of magnitude equivalent to the natural fluxes in those systems. So you see the Colorado River, for example, many years not delivering any water to the ocean. So it's no longer the icing on the cake. The anthropogenic influence in the water cycle is very often equivalent to the influence of natural fluxes. And then, as I've said before, quantifying uncertainties, building an interoperable modular system, and dealing with the need for data assimilation as well. There are lots of science developments, but it's principally about building a community model, and as I think somebody said previously, the best way to build a community model is, and there is a lot of good practice articulated in this area, is not to build something and then deliver it to the community, but to co-produce it with the community that you're building it for. We go around the world preaching that to other countries, and so we should do that ourselves, and so that is what we're doing. We're talking to lots of the people who will potentially be users of this system, and finding out what their particular needs are. I was heartened to hear from the survey, which was reported on at the beginning, that some of the barriers towards using particular models, such as their ease of use or transparency, or finding time to invest in training and so on, are things which we've been funded to look at there. In that light, we've got three particular modes of trying to access this sort of model. One would be for a relatively light user of pre-calculated data sets accessible via a very easy to use web interface. Another would be through the Jasmine. This picture of what looks like a very sophisticated wine fridge is actually the Jasmine system, which runs in Didcot, which is billed as a data-intensive supercomputer. It's linked to the Cedar data store, and essentially brings the computing problem to the data center rather than having users all around the world downloading large amounts of data to their PCs and then two-thirds of the way into their project being able to do some science. So you bring your work to the data center, and part of the way in which it will be set up is that group workspaces on Jasmine will allow collaboration in that way. And then there's a third tier for people who actually want to write new science routines and integrate code into the existing JULES model, and code which would be able to be run in a standalone fashion. So I've just, in the few minutes which I may or may not be allowed, I've just got a few examples of the sorts of things that we're doing, using this Cosmos sensor to diagnose the state of soil moisture from background cosmic radiation, and the neutrons produced by that in the subsurface layers of the soil, and assimilating that information to update the state of our model of soil moisture in the UK. That should result in a 1 kilometre soil moisture product for the UK by the end of this year. Improving river flow routing models so that we've got a national capability to simulate river flood inundation in almost real time, linked to the Met Office weather forecasting capability. UKEP, there is the UK Environmental Prediction Programme, which the Met Office runs, and that's about building these kinds of components into operational weather forecasting, so that we're not just forecasting the level of rivers and the state of the sea independently, but that those two systems are linked, so for modelling things like coastal storm surge and so on. And a national groundwater model, which has been a long time in the preparation, about 1 million boreholes from BGS around the country, bringing those together to form an understanding of where water goes once it infiltrates and recharges our aquifers. I've got one slide left, which I'm determined to get to the end of, principally because if anybody would like to find out more, I'm obviously very happy to talk to people, but we're proposing, we will be having our annual science meeting in London on the 11th of September at the Royal Society, and would welcome participation from anybody in this audience here. Thank you.
Conceptually, will Hydro-JULES assume that over a long term river basins have a water balance that is sort of in equilibrium? I'm thinking of those river basins where the land surface soil moisture is essentially due to mining unsustainably groundwater resources.
Yeah, so that's something which with BGS we're sort of wrangling over at the moment. How deep, essentially, you can frame it as a question of how deep do you have to go before the flux to lower levels of groundwater becomes negligible. Previously, answers to that question have been arbitrary, I think it's fair to say. But with really influential analysis which has been conducted by BGS over the last 5 years, I guess, and it was before my program came online, so I'm not claiming any credit for it. They've used geochemistry to work out the residence time of groundwater at different levels. It's been really useful that there's a series of saline rock strata that are important in determining the salinity and the particular geochemical composition. The short answer is if you go down to 500 metres across the UK, then a lot of the transfers between levels deeper than that are not zero, but are negligible to the point where you can close the water cycle. At the upper level, it's usually the sort of mixed layer in the atmosphere where we're effectively handing over to the atmospheric model. And that's one of the interesting sets of discussions that's going on at the moment, is where to draw the boundaries for interfaces in this kind of approach. It's pretty clear that there is a good physical reason to choose the mixed layer in the atmospheric model, because that's a sort of process-based definition. The trouble is that the height of that varies over time. Similarly with the groundwater, you know, that's a moving boundary too. But if we pick it deep enough, I think we'll get around the problem that you've just described.
One more.
It seems to me you've identified and pretty much solved the problems that there are in building these complex process-based models. And that's the kind of thing which it seems to me the other areas we've heard about, they need to aspire to this kind of modelling expertise. But my question is, do you have a vision as to how the different areas can be put together? Because in the end, that's what landscape decision making is all about.
Yes, it's a flattering statement to make that we or I'm flattered by it anyway, to hear that you think that we've solved some intractable problem. Come back in 5 years and I'll tell you if we've solved that or not. I think there are lots of challenges in this kind of integrated modelling, and the integrated modelling that I'm describing here is integrated sort of biophysical modelling rather than integrated with the human systems, which is where the true problem becomes very difficult. In turn, I'm hoping to draw inspiration from communities in, say, particle physics or genomics and some of the other scientific fields where collaboration has of necessity been around large-scale investments in pieces of infrastructure. Here what we're trying to do is open up the field to solving problems which can't be solved without that kind of collaborative approach, which is why we put so much effort into sort of making this a collaborative activity. I think it's fair to say that in the climate modelling world, that's also something which has worked very well, and we draw inspiration from things which the land surface modelers, the JULES group, and so on have been doing before. It's rather new to hydrology. Well, it's not entirely fair to say it's new to hydrology. There have been lots of activities like that in the past, but I think all the while you have a system which can be understood with a relatively simple model by an individual. It's very, very difficult to move over that sort of energy barrier that exists before you get to work in a collaborative sense. So I hope that we can draw inspiration from others who've taken this path before, and I'm not sure that answers your question, but it's probably about all I can say at this stage.
Okay, can we thank Simon again?